A loaded Boeing 747 is, by mass, mostly fuel. Almost all of it sits in the wings. Not in the body, not in some hidden compartment under the floor. The wings. The reason is not the one most passengers assume. It isn't because the wings happen to be hollow and convenient, or because the engineers ran out of room elsewhere. The fuel is in the wings because the wings need it there. Remove the fuel, and the wing becomes a different structural problem. One that would have to be solved by adding metal, which would force compromises everywhere else on the airframe. This is a decision made by physics, not by convenience. To see why, it helps to look at what the wing is actually doing while the airplane is in the air. In flight, a wing is a cantilever beam. Think of a diving board bolted at one end. It is fixed to the fuselage at its root and unsupported all the way out to the tip. Lift, the force that keeps the airplane airborne, does not act in one place. It is generated along the entire span. More of it concentrates toward the inboard sections, with a steady contribution from the rest. All of that lift pushes upward. Hanging from the middle of all this is the fuselage. Every passenger, every bag, every piece of cargo. The fuselage does not lift itself. It hangs between the two wings, pulling downward at the center, while the wings are being pushed upward at the sides. What this means, in cruise, is that the wings are trying to fold upward off the fuselage. On the ground, gravity has the wings drooping slightly. In the air, the situation reverses. Anyone who has ever sat in a window seat over the wing has watched this happen. The wing flexes. In smooth air, it barely moves. In turbulence, it bounces, sometimes alarmingly, the tip rising and falling in a slow, heavy wave. The first time you see it, the instinct is that something must be wrong, that the wing is about to snap. It is not. The wing tips on a Boeing 787 can flex more than 26 feet above their resting position. That is roughly the height of a two-story building. This is not damage. It is the wing doing its job, but it is also the wing carrying an enormous bending load. And the place where that load concentrates is the wing root, where the wing meets the body. A wing root that had to handle the full bending moment of a loaded fuselage with nothing to counteract it would be a very thick, very heavy piece of metal. And heavier structure cascades. Every pound added to the wing root demands more lift, bigger engines, more fuel, and more wing to hold that fuel. The thing that pushes back is the fuel. A wing tank isn't a single container. The volume inside the wing is divided into compartments running outward from the root. A 747's wings together hold roughly 30,000 gallons of fuel, spread across multiple sealed bays that stretch from the root to near the tip. And these compartments aren't aftermarket add-ons bolted into a hollow wing. The tank walls are the wing itself. The same skin panels and the same internal spars that carry the structural loads also contain the fuel. The structure and the tank are the same object. When those compartments are full, the weight is not concentrated in one place. It is spread along the length of the wing, distributed roughly the same way lift is, but in the opposite direction. At every point along the span, lift pushes up on a small section of wing. The fuel sitting in that section pulls down with its own weight. The two forces partly cancel. What is left over is what the structure actually has to carry back to the root. Without fuel, the entire upward force of lift on the outer wing has to travel inward. It meets the downward weight of the fuselage at the root, creating a massive bending moment. With fuel in the wing, much of that lift gets cancelled close to where it is produced. The fuel and the lift in the outboard sections settle the argument between themselves before the load ever reaches the root. On a fully fueled long-haul aircraft, carrying over 400,000 pounds of kerosene, the bending moment at the wing root drops by a substantial fraction. That reduction is what lets engineers build a thinner, longer, lighter wing. A modern airliner's wing is the shape it is because the engineers assumed there would be tons of kerosene helping to hold it down. This is why the wing fills first and empties last. On most large aircraft, fuel burns from the center tank before the wing tanks, and from the inner wing tanks before the outer ones. The aircraft keeps the structural counterweight in place for as long as it can. And this arrangement comes with a bonus that matters more than engineers like to admit. Putting the fuel out in the wings means it is not sitting beneath the passengers. In a crash, the wings can separate from the body and carry burning fuel away from the cabin rather than into it. The fuel mass also sits close to the center of lift and the center of gravity. So as the tanks empty over a flight, the trim of the aircraft changes less than it would if the fuel were stored fore or aft. These are real benefits, but none of them, on their own, would have been enough to put the fuel in the wings. The bending moment came first. Everything else followed. And this leads to something most people find hard to believe. An empty airplane is in some ways harder on its own structure than a full one. The wings still produce lift the moment the aircraft leaves the ground. The fuselage still hangs from those wings. Without fuel in the tanks, there is nothing along the span pulling that lift back down close to where it is generated, so the wing root carries more. Aircraft are not flown empty often. They almost always carry passengers, cargo, or at minimum a substantial fuel load. But on what the industry calls a ferry flight, an aircraft being repositioned with no payload and only the minimum fuel necessary, the wings work measurably harder for the same maneuver. Imagine a 777 coming out of a heavy maintenance check at the desert facility in Victorville and needing to get back to its home hub in Dallas. No passengers, no cargo, just a flight crew and the fuel required to make the trip. That airplane is operating under a different rulebook than a normal revenue flight. Crews may be given reduced maneuvering speeds, gentler bank angle limits, and restrictions on entering known turbulence. The wing is more exposed without its usual ballast, so it gets flown more carefully. The structural envelope is smaller, not larger, when there is less weight on board. What all of this means in practice is that the wing on a modern airliner cannot be designed in isolation. The fuel system and the structural design are the same problem, worked out together. Every decision about spar thickness and wing taper was made on the assumption that a known amount of fuel would be sitting in a known section of the wing throughout most of the flight. This is not unique to commercial aviation. The same logic applies to military aircraft and large business jets. Anywhere a wing has to carry a heavy fuselage and a heavy fuel load over a long distance, the trade-offs matter. But it is worth looking at how other designs handle the same equation. A fighter like the F-15 carries much of its fuel in the fuselage, with extra fuel pods shaped to hug the body when longer range is needed. A flying wing, like the B-2, does not have a fuselage to fight against in the first place, but the same principle still holds. The fuel is distributed along the span to balance the lift the wing is generating. The logic scales up and down. Engineers reach for the same solution. The fuel and the structure are designed against each other. That is why, when an empty airplane sits on the apron between flights, its wings droop slightly toward the ground. They are waiting to be loaded again. This is not because the tanks need filling, but because the wings need the weight.